Okay, what I want to do today, I want to go through a few typical kinds of examples, because in essence, what you're going to get is you're going to get like the typical 3/4 string problem where something's suspended, it's at equilibrium, or you're going to get a block on a slope with various things happening to it. It's either going to be moving or it's in equilibrium, or you're going to get one where you've got a surface and you've got two different weights hanging over the side. And they're going to have to work out which way the acceleration goes. As a hint, obviously, the moment they say work out the acceleration, calculate the tension in the strings, obviously there is an acceleration. Remember, acceleration, we look for an unbalanced force because it's moving, and that's the force that's causing it to move. Let's just have a look at the and as I say, it's a typical 3/4 string problem where they give us a situation like this, and they say there you go, and there's a string coming down here like so, like that, and they say right, calculate, let's just put this in here, and for example they've said there's a 10 kilogram mass hanging from the knot in the middle. Can you see once again you've got the three strings? It's either going to be there or there, but it's a variation on a theme in essence. So we've got to look for the patterns in this, and that's going to tell us which solution, which method to choose to solve it. Well, what do we do first? We always put in FW over here, and FW is going to be equal to 98 newtons. Right? That's what we always do first, put in the FW. Now I'm going to split this up here. I'm going to call this tensile force there T1, and the force in the string here of T2. Okay? Then they've said for us, for example, they've given us a 45 degree there, and perhaps they gave us 30 degrees over there. Okay? Now, what do we do next? Well, we've got two forces that are unknown that are acting at an angle. Remember, when we have forces at an angle, what do? We find the horizontal and the vertical components of the forces every single time, because we don't work at an angle. We don't need to, because when we've got a component, we can add the components. Right, let's just take out this force here of T1. Right, you can see here, there's T1 come out. Now, let's have a look at, change of color. Let's have a look at the force components, right? Remember, take our angle with us, 30 degrees over there. So if this is T1, across is going to be equal to, its opposite, remember, is T1 sine of 30 degrees. And the one at the bottom is going to be T2 cos of 30 degrees. Now we put in the numbers. Well, we know what sine 30 is, and it's going to be 0.5. That's 0.5 T1, and cos of there is 0.866. 0.866 times T2. Right, let us move to the other side and take out our other force. We've got T2 acting up there, and once again, let's take out the components of those. There we go, there's one, and there's the vertical one. So this is going to be T2, and remember that's our 45 degree angle over there. It's going to be T2 cos of 45 degrees and T2 sine of 45 degrees. If we work those out, we get that it is 0.7071 T2, and this one is 0.7071 T2 as well. Right? Now, what is the next step? The next step is, as we would always do, we say, right, let's look horizontally and vertically and see what's happening. Is there an unbalanced force horizontally? Is there an unbalanced force vertically? If so, let's find it. But in this case, they've already told us it's at equilibrium. What does that mean? It means that the forces up must be equal to the forces down. Forces to the right must equal forces to the left, so that we don't move. So let's have a look. Let's just do that. Although we don't know the numbers, let's just put them together. Okay, let's have a look first of all at, let's take horizontal, shall we? Horizontally, Right? Now horizontally, let's have a look. What have we got? We've got a force to the right over there of 0.866 0.866 times T2. See that one? That's the force there acting to the right. Now, let's have a look. What is acting to the left? Because it must be equal. To the left, we've got a force 0.7071 T2. There it is. 0.7071 T2. And what can we do with that? We can rearrange it so that we've got, look what I've done. I've written T2 there instead of T1. My bad. This is T1. That's a T1 over there. So we can now put them equal to each other, and at the end of the day we can then say that T1 must be equal to 0.7071 divided by 0.866 T2, which gives us 0.8165 times T2. Right, then we move along. Now we have a look at vertical. There we go. Vertical forces. Now remember, we've got this guy acting down. So the ups must equal the downs. So let me just put the down over here. 98 newtons over there. That's acting down. Now let's see what's acting up. Now you'll always have two because there's two strings. So there's two vertical components. So we've got there T2 sine of 45 degrees, which is this one over here. And over here, T1 sine of 30. T1 sine of 30. Those two we add together because they are both acting up. Now, let's have a look here. If we rearrange this, we're going to have to make a substitution of T1 into this equation. So what do? We put T1 into the equation, T2 into the equation. We end up fundamentally, this guy here is going to be 0.5 times T1 plus 0.7071 T2, and that's going to be equal to 98. Now we make the substitution for T1, and that's going to be 0.5 times 0.8165 T2 plus 0.7071 T2 equal to 98. Therefore, multiplying this out, simplifying all of this, we end up with 1.1154 times T2 going to be equal to 98. And we can now work out that T2 is going to be equal to 87.86 newtons. What do we do with the T2? We substitute it back in there, and we calculate then that T1 is going to be equal to 71.74. Okay. Now, in all of that, all we did is we didn't have certain numbers, so you just leave them as their unit, T1 or T2, or if for example, they said calculate the maximum mass, and they gave us maybe a maximum force in the strings. Can you see that the recipe is identical? It doesn't change. All we do is we take the forces up, we resolve them at an angle, and then we put them equal to the up, equal to the down, to the right, equal to the left. So it doesn't matter how we structure that kind of problem. Essentially, it stays the same. Okay? Let's take a slightly different problem, shall we? Let's have a look at a block acting, or block sitting on a slope over here. Now this is a slightly longer problem because what I want to do is I want to go through all the different phases of it, right? So what do we have to do first? Let's have a look. If they say to us, for example, you have a 10 kilogram block resting on a surface which is at an angle of 20 degrees, and they give us mu. Remember, if they give you mu, we're always going to go and calculate it. So what is the recipe for these blocks? First thing you do is in physics we make a drawing of what we've got. Well, let's make a drawing of this guy here, our block on the slope, and I've done this previously, so let me just take it here. Right, they've said I'm exaggerating slightly on the slope, 20 degrees, and here's our 10 kilogram block. Right, we say, right, you weigh 10 kilograms over there. And now the very first thing we always do is we put in FW, which in this case acts vertically down like that, and FW is equal to 98 newtons. Correct? Okay. The next step. Now we haven't even read the problem yet. All we're doing is we're doing all the preparation work in order to be able to address this problem. Let us now put in, remember we said the next thing we do is we put in these components. Remember the 90 degrees is there, guys. This is 20 degrees over there. What is this one? Well, stand at the angle and look again. That's the opposite, so that must be 98 times sine of 20 degrees. Okay? Ditto, we find this one, and this one is going to be 98 cos of 20 degrees. And if we work that out, okay, we'll get to that 98 equal to 92. And this one down here is 33.5. Right? What's the next thing we do? We put in F normal, right? So let's put in F normal now. Let's go back to black. So right, there's F normal. F normal is going to be equal to 92, isn't it? It's the equal and opposite force from the third law on the slope. Then we transfer this force here to down the slope, and we say 33.5 newtons acting down the slope. Remember, they told us that if for this problem mu equals 0.15, we see mu, we calculate FF. FF is equal to mu times F normal, which is going to be 0.15 times 92, which is going to be, let's have a look, 0.15 times 92 is going to be equal to 13.8 newtons. Okay? Right, now we've pretty much got everything. We've drawn it, we've done the basic work, we've put in our force, we've put in our components like that to the force, and we've put in F normal, and we've got FF. Now, the first thing we say to ourselves is, if the first part of the question is, for example, what happens to the block? Well, what do? We look at it logically and we say, well, what does the block want to do? The block would want to go down the slope, wouldn't it? So, then what we do is we say, right, pretend that the block is going down the slope. And put in friction. Which way is friction going to be? That way, isn't it? Our friction is going to be going in that direction. Why? Because it's going against the direction of movement. So we say FF over here is 13.8 newtons. Okay? Now, next thing is to say, right, we now have to look and see what is happening. Is there a resultant? In other words, will the block go down the slope? Remember, what is the block? It's sitting over here, right? Here's one. It's sitting over here on the slope. There's friction which is holding it back. The block wants to move down because of the component of weight down the slope. Right? So let's have a look. Let's look. You can do it how you particularly want to, but let's say down slope, this side, okay, and up slope, that side. Up the slope, we've got 13.8. Down the slope is the 33.5. Downslope is bigger than upslope, so let's call downslope positive and subtract this one, and we end up with 33.5 minus 13.8 is going to be equal to 19.7 newtons, and that is down the slope, right? And we'd put downslope right? What is that? It's a resultant, isn't it? And the moment we've got that, we go back to F net MA, and we say F net is 19.7 is equal to 10A. Therefore, A is going to be equal to 1,97 meters per second squared, and we must give it a direction down the slope. Well, that's the situation if there's no other forces acting on the block, right? It's just the block on the slope itself. Now, let's take and put a piece of string and say, right, how much would we have to pull if we were holding it on the slope? So, before we do anything, let us just take this one away here, because remember, friction we always have to look at for each and every individual case. So what have we got now, right? We've now got a situation where, get my slope over here, my soap on a rope again. Can you see over here, this was what we had originally. It doesn't slide. It wants to, but the friction is enough. Here's where we had it with an F net down the slope. Watch that again. The friction is holding it, and there's an F net down the slope. Right. Now we complicate matters and we say, right, there's our block. Now someone's going to stand up slope here and hold it. There we go. I'm now holding it so that it can't slide down, right? But look at it, just wants to keep going, which means friction is still acting up the slope. Friction is helping us, right? Because that is the minimum force that we need to exert just to keep it in equilibrium. Note the change in wording. It's now in equilibrium. So what do we say? We say, right, we're now going to have another force coming in. Let's put this one in red just for that. We say, there it is. The T. They want to know what the tension is in that force. So let's now do our equilibrium again, right? Let's just move it slightly up, right? And let's do it over here. Okay. We've got upslope. Upslope, we've got T, right? That's our tension acting up the slope. That's the rope. But at the same time, acting up the slope, okay, we've got FF is equal to 13.8. Do you see that? In other words, friction is helping us, because originally it was just sliding down the slope. Now it's just stable on the slope itself. So upslope, we've got plus 13.8 newtons. Okay? And what must that be equal to? Downslope, which is 33.5 newtons. Therefore, the tension is going to be 33.5 minus 13.8 is going to be 19.7. Right? The interesting thing now is, let's have a look. Can you see that? Originally our F net down the slope was 19.7. Now, what have we done? Actually, we've calculated the equilibrium to F net, haven't we? We've said, right, I will cancel you out. So therefore, what do I have to do? I have to pull upwards with exactly the same as F net was down the slope. The next question is where they say, calculate the maximum force, the maximum T that we can put onto the slope, onto the box, before it starts moving. Implicit in the word maximum is we pull, and all of a sudden it's going to start moving. But what has happened now? In this scenario, remember, we have to go back to our friction again, and we say, let's remove you. Next question is, right, maximum force. We've still got T, okay? Now what do we say? I just want to scroll this up. Okay. Oh, but before I do, let's go back to it. Remember, we've now got to put in our friction. This T is now pulling up, isn't it? We're bigger than just holding it. We are about to move it. This is what happens now. Friction is now acting against us, isn't it? Because we're about to move it up the slope. So the body wants to move the block, the box, whatever, wants to start moving up the slope. So friction is reversed. It's acting opposite direction to the movement that it wants to take. So now what we do, so okay, now we say, let's take our upslope again, shall we? Just put this in here. Let's take up the slope. That's not a T, it's an L. Up the slope, what have we got? We've got now, let's roll it back. Up the slope, we've got T, but that's the only thing acting up the slope. Down, we've got the weight and we've got friction. Okay, we've got the weight and we've got friction. So upslope, we've got T, okay, and downslope, we've got the friction. I think I'm right, 13.8, and we've got plus 33.5. So if we add those, we get 33.5 plus 13.8 is going to be equal to 47.3. 47.3 newtons. Okay? So, now, we've found what happens to the block if it's just left there. Is friction enough to hold it? No, which means there's a resultant, so we've got an F net, which means we've got an acceleration down. Then we've put a string, we're holding it now, but friction's still helping us. We're not pulling it, we're just holding it. We're balancing out that force down the slope, remember? The next one is we start pulling, and friction turns around and starts acting down the slope. Okay? Right, now, so therefore, if we pull with more than 47.3 newtons over here, what's going to happen? Well, with more than 47.3, the block is going to start moving upslope, isn't it? Let us say we pull with 50 newtons up the slope, right? So now, let me just take my drawing down and let's put it in once again. I'm going to take out friction as a rule. We can now put in that they've told us that the force up the slope is 50. All right? Just remember in the previous problem over here, at this point here, we can put an equal sign because it's in equilibrium, it's not moving still. Now let's have a look at our upslopes and downslopes again, shall we? Let's move it down slightly. Okay. Right. Let's have a look. Up the slope, down slope. Now, up the slope we said we've got 50 newtons acting. Now let's have a look and see what is acting down. Down the slope, right, is we've still got our 33.5, our mass, and we've got, let's see, what is friction going to do? Friction is going to act against it of FF equal to 13.8 newtons. So friction of 13.8 is also down the slope. Let's go and put that in. We've got down the slope, 13.8, and we've got our 33.5 newtons, which is the weight acting down the slope, right? Now, let's have a look what is going to happen now. In essence, what have we got? We've got, I can't put them equal anymore because up the slope is more than down the slope. So I subtract to give us an F net. And what do we get if we work this out? Let's just go on with it. Okay. F net is going to be 50 minus that lot. Let's see. 50, I've worked it out here. It comes to be 2.7. What do we do when we see an F net? Straight away, we say, right, F net must be equal to MA. Therefore, my 2.7, okay, must be equal to 10 times A. Remember, it's the mass. So therefore, my acceleration is going to be 0.27 meters per second squared, and I must give them a direction. Up the slope, right? Okay, so those are two basically quite advanced ones where we don't know the tensions in the strings. We have to work them out in the three-force model. This one here, we've done all of the possibilities that you can have, from accelerating down the slope to balance just wanting to go down, to balance just wanting to go up, and the last one where we've got a force acting upwards, which causes an acceleration up. The next one that I'm going to do is where we've got on a plane, right? And they want to fall off the table, stay on the table, and we're going to look at what's going to happen in that situation. They're going to be joined by a string, and we're going to work out what the accelerations are between them. Okay? So essentially, with all of these, all we have to do is follow those recipes. Let's have a look at the next one, which is then going to be the body which is on a table. So we'll do that in the next session.